Okay, so today we're going to actually start on the second chapter, which is going to round out the Euclidean approach to these things. So actually later I'm going to add to the syllabus page a nice online version of Euclid's Elements. It's really, really convenient. Of course, it's nice to have an actual, hard copy of it as well, but there's a nice, convenient translation of it that you can have a look at that, like I said, I'll add to the syllabus page, and that helps when a lot of times in the lecture I'm going to refer to things that Euclid does in the Elements, so it'll make sense if you actually have it in front of you. Also, it's kind of neat to I'll be referring to propositions and proofs that Euclid does, and it's kind of neat to think about using a book that's like 2,300 years old as a textbook in that way. But it was literally kind of sort of the first textbook ever, so that's one of the appeals. Okay, so now the topic of chapter 2 is Euclid's axiomatic approach to geometry. So as I already mentioned, basically we're going to go through over the course of this chapter kind of all of the things that Euclid introduces as his axioms, and I'll isolate the most important thing right off the bat. But I've already mentioned that there were some holes in Euclid's axioms that didn't quite cover everything, and so to make this like 100%, completely rigorous, David Hilbert, many years later, so almost 2,000 years later, filled in the gaps with a complete axiomatic treatment that filled in the last remaining gaps of Euclid, so that if you wanted to, approach Euclidean geometry purely from an axiomatic standpoint, so if you think about developing this in the same way that set theory was eventually developed and all the foundational, fundamental stuff, when it came to, the underlying, like foundational stuff that math was built on, you could actually do that in the exact same way for Euclidean geometry. So, what is the most important thing? It's the parallel postulate, or this textbook calls it the parallel axiom. So this was Euclid's fifth postulate. Like I said, the textbook calls this the parallel axiom, or Euclid's fifth postulate. Why does it say first? Fifth postulate. So this is definitely the most important, as I've said before. So this is the single thing that makes Euclidean geometry Euclidean geometry. Okay. And what I mean by that, and again, this is something that we're going to talk about throughout the course, because this was the central thing that drove developments of newer geometry, was exactly a consideration of how to prove the parallel postulate, because Euclid includes it as a list of his postulates, but he actually doesn't need it until I can't remember exactly what proposition this is first used in, but he doesn't need it for a while. So this is not something that he needs in when he's setting out his geometry. He doesn't need it for a little while, and the reason that it was included, and especially if you compare it to the other axioms and the other postulates, it is more complicated than the rest of them. And the thing is that it is, interpreted that Euclid and most other ancient mathematicians felt that the parallel postulate could be derived from the others. But they didn't quite see how to do that, and so they included it as an assumption, even though they probably thought that it could be, if you were smart enough, you could actually prove it from the other postulates. But it turns out that after thousands of years of attempting to do that, it was found that that's not possible because it is actually independent of the other axioms. So what that means is that there are systems of geometry where all of the other common notions or all the other postulates of Euclidean geometry are true, but the parallel postulate's false. Okay, so this is the key thing that drove investigation into non-Euclidean geometries. Okay, but it turns out that this parallel postulate is actually equivalent to a lot of the things you think of immediately when you think of Euclidean geometry. So if I ask you to rattle off a list of facts that you consider to be kind of like central to Euclidean geometry as you learned it, a lot of those facts that you state would actually be equivalent to the parallel postulate. So for instance, if I told you, say, or if I asked you, what is the interior angle sum of any triangle? Well, I'm sure that if we were in person right now, all of you would say, 180 degrees, or it's pi, right? Pi radians is the answer to that. Like, what's the interior angle sum of a triangle? It's 180, or it's pi. But it turns out that fact is not true in the other geometries that I mentioned earlier. So hyperbolic geometry, elliptic geometry, that neither of those facts, that's not true. But in Euclidean geometry, it's always pi. That interior angle sum is always pi. So what's the difference? Well, the difference is the parallel postulate, as we'll see. So we're going to actually prove that fact, and you will see how it, at least the proof that we show, is going to very much rely on that. But it turns out it actually relies on it regardless of what proof you go with. So Euclid's parallel postulate. All right, so the Greeks use postulate interchangeably with axiom here, or I should say the Greeks didn't really. This is interpreters doing this. But so Euclid's parallel postulate is the following. So if a straight line, or if a straight line crossing two straight lines makes the interior angles on one side together less than two right angles, then the two straight lines will meet on that side. Now, it turns out that this statement is equivalent to a number of other statements that we can make. That depending on the context, some of those other forms of this might be more or less convenient. We're actually going to use this form usually, because for our purposes this will be more convenient, but the one you might be the most familiar with is a form called Playfair's axiom, which is equivalent to this, and I'll state that in a second. But I want to draw this situation here. So I have two lines, we'll call L and M. So here's my line M, here's my line L, and I have a straight line crossing these two straight lines. So this is my line N. Okay, and it says if it makes the interior angles on one side. What are the interior angles? What do I mean by that? So I mean a pair of angles that are inside. Okay, what that means, for instance, is if this is an angle in question, the other interior angle is this. Okay, it is beta here. So alpha and beta, these are the interior angles on one side. If these are taken together, that is their sum, if their sum is less than the sum of two right angles, then the straight lines meet on that side, and you can see from this picture that that's apparently what's happening, right? Okay, so I have two lines, L and M. Since these interior angles sum to be less than the sum of two right angles, those two lines are going to meet on that side. That is my parallel postulate. Okay. Now, you might look at this arrangement and say, how could this work out in any other way? How could it be? Like, you might even, torture yourself by drawing various configurations here over and over again, and you just say, I don't see how it could be any other way, right? Why do I even need to assume this? It just seems like this is always true. Right? If I have the same idea of what a line is and what angles are, it just seems like this always works out like this. But we will see later, I'm not going to do it now, but we'll see later how this fails in those other settings. Okay. It turns out the way that it fails is what your notion of line is. Okay. The idea is you have an idea in your mind of what a line is, but of course, like geometrically, what's the most important thing about a line? It's not the way that it looks, it's what it's doing. Right, so that's the first hint that things are going to be a little bit different here in other settings. So anyway, so this is the picture. Okay, so note that if they do not meet, right? So if L and M do not meet, and M do not meet on a side, then alpha plus beta is what? Alpha plus beta has to be pi. Okay. All right. And i.e. they're parallel, right? L and M are parallel. That's all that's saying. So alpha and beta together make a straight angle, is what is being said here. Okay. And so it turns out that in that case, right, what is this picture? What does this picture look like? So in that case, this picture is actually the following picture. So here's my line N, here's M, and here's L. So my picture looks like this. So this is alpha. This is alpha. This is pi minus alpha. And this is pi minus alpha. All right, so whatever these angles are, they are pi minus alpha. Okay. Now, how do I get that? How did I get this from that setup? Let's go back for a second. Well, this is just simply if they don't meet on a side, then what we get is that that is, if L and M are parallel, then alpha plus beta is equal to pi. So beta is pi minus alpha. So I can replace beta in that case with pi minus alpha. But if this angle is pi minus alpha, then the angle lying on the straight line with it has to be alpha. Similarly, this angle lying on the straight line with alpha has to be pi minus alpha, right? So that they sum to pi. Okay, and so this is actually the picture I get. So if L and M are parallel, this is what I get. So if L and M are parallel, this is the picture I get. Okay. Now this is going to tell us a couple of nice things. So one, it's going to tell you that in this configuration where these lines are parallel, these two angles coincide, or these two angles are congruent. They are the same angle. Now we'll have a name for those. We'll call them alternate interior angles. Okay. And it turns out that when L and M are parallel, there's this configuration of a third line cutting across them. Alternate interior angles are congruent. Okay. This fact is equivalent to the parallel postulate. Okay. All right. So, what's another? I should say, what's another thing that I can get from this? Note also that any line through the intersection of n and m not meeting L makes the angle pi minus alpha with n. Okay. Okay. But the intersection of n and m is it's this point, right? So if you have a line through this point, not intersecting L, making angle pi minus alpha with n, that line has to just be m, i.e. the line equals m. Okay, that might seem like a very obvious thing that you said there, but really what this is saying is that the parallel to L through a given point exists, or if the parallel to L through a given point exists, it is unique. Okay, i.e. if a parallel to L through a given point exists, it is unique, meaning there's only one, right? Okay. So, using this setup of the parallel postulate, we've shown that if a parallel to L through a given point exists, then it's unique. Okay. Now, how can I show the existence of a parallel to L through a given point? Well, you might say, oh, I've constructed things like this before. Okay, but we can use what's called ASA. We'll get to later. To show the existence of a parallel to L through a given point. Okay. Well, we'll wait. We'll come back to this. So we'll come back to this. So what is it that I've been doing here, spending time on this? What I've been doing is that thus existence and uniqueness of of parallels to a given line through a given point not on the line follow from the parallel postulate. But also, this implies the parallel postulate. So really what I'm saying, thus, the parallel postulate is equivalent, That means equivalent logically. It is the same statement. So whether you use the parallel postulate as I wrote it before, or whether you use this fact I'm about to write, you get the same resulting geometry. So thus the parallel postulate is equivalent to the modern parallel axiom, which is also called Playfair's axiom. So what is the modern parallel axiom, or Playfair's axiom? This is for any line L So for any line L and point P not on L, there's exactly one line through P that is parallel to L. Okay. Now, for a number of reasons, this can be a more convenient form of the parallel postulate. But it turns out that for a lot of our uses, the parallel postulate, as we want to use it, we actually want to involve the angles. Notice this doesn't involve any angles, apparently, right? All it talks about is the existence and uniqueness of a parallel line to a given line through some point that's not on the line, right? So this references no angles explicitly. Okay. But sometimes we actually want to talk about the angles that result from these parallel line configurations. And so this is actually not always going to be as convenient for us as the original formulation. So the other thing that I want to note is going back to this picture. When you are in the parallel configuration here, we call these angles alternate interior angles. So these are called alternate interior angles. Okay. So another way that we could state another way to state the parallel postulate, and you could think about why this statement would be equivalent to the original parallel axiom or parallel postulate, is the following. It's alternate interior angles formed by parallel lines are congruent. Okay. You might remember, maybe in your geometry course in high school, alternate interior angles were defined to be formed by parallel lines. So whenever you were saying the words alternate interior angles, you were only talking about the case where the lines are parallel. So you might remember the phrase alternate interior angles are congruent as one of the things that you could use in high school geometry. Okay. All right. And so this is actually an alternative formulation. And we'll see why these formulations that involve actually mentioning angles can be nice, because we're going to be able to use that. So first things first. First application of this. So first use of the parallel postulate. Turns out that this is not, we're not using too much machinery here. What we are doing is intimately related to the parallel postulate. So angle sum of a triangle. Okay, so if alpha, beta, and gamma are the angles of any triangle, then alpha plus beta plus gamma is equal to pi. So this is the very familiar phrase that the interior angle sum of a triangle is 180 or pi radians. So how to prove this? Well, I draw a triangle. Okay, so let's draw a triangle here. So let's okay, so I almost drew an isosceles triangle again, despite not wanting to, but let's say here's alpha, here's beta, here's gamma. Okay, so what is the idea here? The idea is that I could extend this side. Okay, this line segment I can extend indefinitely to be some line, whatever. Okay, once I've done that, I have line and I have a point that is definitely not on that line. So through that point, I can construct parallel. Okay, call this L. So here's my line that is parallel to this thing here. The way that I've drawn it doesn't actually look parallel, but it is. Okay, so here's my parallel line. Well, now, if to aid in my visualization, I can extend the other sides here of this triangle. And so I have a line L. We can call this line corresponding to my opposite side of the triangle here M, and they are parallel. Okay, but if they're parallel, then by any of those previous formulations of the parallel postulate, what do I know about these new angles formed up here by L with the other sides of the triangle? Well, what is this angle? It has to be alpha. And the reason that has to be alpha is, one, you could say this and this are alternate interior angles, and since we labeled this alpha, this has to be alpha. Because L and M are parallel, so these form alternate interior angles, and alternate interior angles are congruent by the parallel postulate. Okay, similarly, this has to be gamma for the same reason, because this forms alternate interior angles between the parallel lines L and M and this line. Okay. Well, what does this say? These angles lie on a straight line. So alpha plus beta plus gamma is pi. And that's it. So that is really, really closely related to the parallel postulate. It turns out, this is, as I mentioned, this is absolutely not a coincidence at all. In fact, there's many deep, going very far into geometry that looks nothing like Euclidean geometry. There's some very deep statements that basically say comparing triangles in a space tells you a lot about how the geometry is going in that space. And so just looking at something like the angle sum of triangles tells you a lot about the type of geometry or what you can expect from the geometry that you're studying. Okay. All right. So that's that. Okay. So next, I want to discuss congruence axioms for triangle. Now, conceptually, there's some issues in dealing with triangles, and I bring this up every time I teach any course that is 300 level or above course, I typically bring this up when I'm talking about equivalence relations, like in Math 310 or something, when equivalence relations are first introduced. There's some subtlety going on where I can have two triangles, right? So here's one, and here's another. Okay, I didn't do that great of a job making these triangles. I meant these to be actually congruent triangles, but let's forget about that for a second. Suppose that I did a better job drawing these, and these were clearly congruent triangles. Okay, so I haven't even said what congruent triangles means yet, right? So maybe I shouldn't even say that yet. I'm just going to say, look at these triangles. Are they the same triangle, right? What do I mean by the same? Are they literally the same triangle, right? Clearly not. There's one. There's the second one, right? This triangle's here. This other triangle's over here simultaneously. So they can't be the same triangle because I can point to two triangles separately, right? They occupy distinct locations on the page, so they clearly cannot be the same triangle. Okay, if we're talking about that. But that notion of equality, which is the same notion of equality that we use for numbers, right? So when you have two real numbers that are equal, well, then they occupy the same point on the real line. So if I were to plot those on a real number line, they would be in the exact same position, right? So if we thought about equality meaning same position, right, then equality of numbers is exactly what we mean by when we say same position, and that is the notion of equality we use for numbers. But this is too rigid when we're talking about things like triangles and other geometric objects. It's too rigid because what we're interested in when we talk about a triangle is not the location where the triangle is. What we're interested in are the side lengths and the angles, right? So we're interested in for two triangles, 6 pairs of things are what we're interested in, 6 pairs of data. Okay, but for a single triangle, it's just 6 things. It's 3 side lengths and 3 angles. Right, so it turns out that really what I want to talk about when I talk about a triangle and I want to study properties of a triangle, so I want to talk about triangles and all triangles that are congruent to it. So maybe I have this triangle and a triangle over here that's congruent to it, but I want to save time and only study one of them because I recognize, oh, like all the other properties are the same, I've just moved this triangle in some way. That's nice. So I've just slid the triangle over, I've just rotated the triangle, I've just flipped the triangle, I've just done one of these isometries. The problem is that when I start wanting to introduce motion and isometries and stuff that I haven't even, really defined yet, it gets a little tricky. So I want to avoid doing that. So then how do I talk about congruence of triangles? What is the definition? Okay, so definition of congruence. So we say two triangles are congruent when their corresponding side lengths and angles are all equal. Okay. Meaning that if you have triangle ABC and A prime, B prime, C prime, you've lined them up, or you have labeled them in such a way that side AB corresponds to side A prime, B prime. Why am I doing this with words? I can do this with pictures. So let's say that I've done it like this. So I have A, B, C, and I have A prime, B prime, C prime. Okay? So in this example, it would mean the following 6 things. It would mean that side length AB is equal to side length A prime, B prime. So what I mean by corresponding side is this side corresponds to the side A prime B prime over here, right? Okay, and the side length AC is the same as the side length A prime C prime, and side length BC is the same as side length B prime C prime, and the angle at, so if I have alpha, beta, gamma, and alpha prime, beta prime, and gamma prime here, then alpha is equal to alpha prime, beta is equal to beta prime, and gamma is equal to gamma prime. So if two triangles are congruent, I get these six statements, okay, about these quantities. Okay. Now, this is the definition. It's perfectly fine, nothing wrong with this. But practically speaking, I'm going to want to be asking the question of whether two given triangles are congruent, and it turns out that this is just a lot of info to check. Okay. In fact, it's so much info to check. The question becomes, could I shortcut this? Do I have to know, if I were given two triangles, say I only knew like this info that I boxed, so I didn't know that the last angles were congruent. Is that enough? Right? Is that enough? Well, you might be able to say, from the equality of these things and that previous theorem that I used, I could get that these angles are congruent, so that would be enough. Right? The question is that enough? So if I include less, right? If I only had this info, is that okay? Yeah, it turns out that that's okay too. Okay, in fact, what if I only had that all the corresponding sides were equal? Is that okay? It turns out that even that's okay, but I can't toss out more than that. Okay. What if I only had two of these lengths being equal, but I had one of these angles being congruent? The answer to that is that it actually matters which pair of angles I have. I need the included angles here. Okay. What am I doing here? These are the congruence axioms that I'm mentioning. They're going to be axioms for us because to prove them, I would have to do a little bit of hand waving as regards to motion, which is exactly what Euclid did. We're just going to assume them to make it easier. Okay. So exactly what we're going to assume is the following. So Euclid uses the following, and what it is the way that he, this is proposition 4, book 1 of the Elements. So this is if two triangles have two corresponding sides equal, and the angles between these two sides are equal, then their third sides and the corresponding two angles are also equal. I should say the third sides and the other angles are equal. Okay. This is side angle side. Okay. So this is SAS, or side angle side. Oh, I'm off the page. There we go. Okay. Okay. Now, what is SAS, or side angle side? Let's just rephrase this. So this is our SAS axiom. Okay. So if triangles ABC and A prime, B prime, C prime are such that the side length of AB is equal to the side length of A prime, B prime. Angle ABC, this means that the vertex of the angle is B, if you remember from high school geometry, is equal to angle A prime, B prime, C prime, and side length BC is equal to side length B prime, C prime. Then also the side length AC is equal to the side length A prime, C prime. Angle, so this is the third side is also equal, or the third sides are also equal. Angle BCA is equal to angle B prime, C prime, A prime, and angle CAB is equal to angle C prime, A prime, B prime. Okay. Okay. And so you don't have to remember that this is going on. The easiest way to remember side, angle, side, there's a reason why we abbreviate it like this, is that it's if two sides in the included angle, so if two sides in the included angles are correspondingly, equal between two triangles, then the two triangles are congruent. Okay. From SAS, we can deduce angle side angle, which is the corresponding axiom for angle side angle instead. So two angles in the included side, you get the exact same kind of thing. Okay, and we can also deduce side, side, side. So these are the three triangle congruence axioms. Okay, now the thing is that we only need to assume one, we can get the others, but just to make this easy, we could assume all of them if we wanted to. If we're not trying to be mega efficient with our list of axioms, we could just assume these as well. Turns out that it's the same thing, but you can actually prove angle side angle and side 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 from side angle side. Okay. So here is note. Side side angle is not a congruence axiom. Okay. And this will be in your next homework, which I'll post later today. So come up with an example that shows why. I apologize if you heard my cat puking. He'll probably be puking a bunch because that's what he does. Okay, so that is something that I should mention, is that these are the three triangle congruence axioms, and side-side angle is not. Okay, so what do I want to do with these? So first things first is I want to show a nice fact about isosceles triangles. So here's a theorem. So it's the isosceles triangle theorem. So what's isosceles mean? Iso means same. The celes part means side. This means same side is what this is supposed to say. So an isosceles triangle is a triangle that has at least two congruent sides. So if a triangle has two equal sides, so two sides of equal length, then the angles opposite these sides are also equal. Okay. So let's prove this. This is a proof due to Pappas. Okay, you're going to recognize his name in your homework, and throughout the course I'm going to be referring to Pappas. Pappas is basically the last geometer that knew what he was doing before like the Middle Ages. So there was a giant gap of about 1,000 years after Pappas where no one knew what was going on. So okay, so what was Pappas's proof? Basically, it was note that ABC and the triangle ACB are the same triangle. What? What is that? Well, here's ABC, and here's triangle ACB. Oh, no, that's not what I wanted. There. Okay. All right. These are really bad triangles. All right. So here's two triangles, ABC and ACB. They're the same triangle. I just reordered the vertices, but this is what it means when you're doing that, right? I just drew the triangle this way instead of this way. Okay. Well, since they're isosceles, since ABC is isosceles, the length of AB and the length of AC are equal. i.e., well, writing it less stupidly, these two side lengths are equal. Right? Okay. But then I have two equal sides and the included angle at A is also equal to the included angle at A. Right? What am I saying? So if you remember in geometry, right, like in high school, you would maybe mark these. So you'd say, okay, these two sides are the same in this triangle. It's an isosceles triangle. Okay, but then coming over here, well, it's the same as these two sides. This is the same triangle. And in fact, at A, they share an angle, right? That angle at A is the same angle at A because it's literally, it's the same angle. That's why they're equal. And so in this triangle, I have two sides and an included angle are equal to two corresponding sides in the included angle. So by side angle side, these triangles are congruent. Are congruent, okay, i.e., all other corresponding quantities are equal. But look at the correspondence here. I've just flipped these two vertices B and C, i.e., the angle at B is equal to the angle at C. But that's exactly what I wanted to prove. Right? Okay. All right. So these angles opposite the equal sides are also equal. So B and C are also equal. So this is a nice use of side angle side to get this done. Okay. It does it really quickly. There's another way you could have done this. In fact, I'm going to have you do that on your your third homework, which I'll assign like a day before your second homework's due. So your second homework's going to be due on Thursday. It'll be due Thursday night. I'll assign your third homework on Wednesday. So anyway, and I'll do that. I'll assign that after my next class. So here in like another hour and a half, I'll assign your second homework. Anyway, so that's all I wanted to do for today. So we'll continue on with Chapter 2 stuff. We'll probably mostly finish, probably won't entirely finish Chapter 2. Yeah, we won't entirely finish Chapter 2, but we'll finish a good chunk of Chapter 2 on Wednesday. By the end of the week, we'll have finished Chapter 2. So anyway, that's the plan. So I will see you all on Wednesday.